Okay, so let's run through these so that you know what your answers should have been. So number one was asking about the thermal capacity of an anode and what material can be added to it to increase the thermal capacity and serve as a heat sink. So that's the key word there. You're increasing the thermal capacity by adding a heat sink. So that would be graphite. The reason molybdenum isn't a correct answer if you happen to put molybdenum is because all anodes contain molybdenum. Molybdenum reduces the weight of the anode. It does have a role in thermal capacity. Otherwise, we wouldn't use molybdenum. But all anodes are manufactured with molybdenum. So the answer that it was looking for, or that I was looking for, is graphite. And it's because you're increasing the thermal capacity. What can you use to increase the thermal capacity? What material serves as a heat sink? So that would be graphite. So CT and interventional would use that type of material backing. So they would still have the anode that has the tungsten and the molybdenum, but the addition of graphite is a heat sink. So graphite's classified as a heat sink. So any questions about number one, why it had to be graphite, not molybdenum?
Could you explain why it's not molybdenum?
I can't hear you, Sierra.
Could you explain why it wasn't molybdenum again?
Because molybdenum is found. Molybdenum is standard on all anodes. Because the key here, it's to increase the thermal capacity and serve as a heat sink. So that's why it's graphite. For number two, it's looking at what determines the maximum MA and time and KVP that you can use for a single radiographic exposure. And you had to select two answers for this one. So it's referring to the tube rating chart. And so I gave you, three of the things here: MA, time, and KVP. What determines MA, time, and KVP that can be used? Well, the other two factors that you need when you look at a tube rating chart are what? What do you need? What other information do you need for the single tube rating chart to see if the MA, time, and KVP would be safe? What other information do you need? What do you need? What else is on that chart? Let me give you your answers here and you'll see. So there's anode speed, actual focal spot size, space charge effect, or source to image distance.
Would it be anode speed and actual focal spot size?
Yep, anode speed and actual focal spot size. Space charge effect has nothing to do with whether or not the exposure is safe or not. The space charge effect, that has to do with why vendors do not manufacture X-ray equipment above 1200 MA. Okay. So anode speed and actual focal spot, you have to know those two factors to know whether or not MA and time and KVP would be safe for that particular X-ray unit. Okay. And then for the third one, let's see. Metal deposits. What causes metal deposits in an X-ray tube? What causes metal deposits?
Filament vaporization.
Filament vaporization. As that filament heats up, it releases metal gases and it settles onto the inside of the tube, and it'll cause that discoloration. And that happens as a tube ages. Tube ages. Okay. So metal deposits does not result from rotor bearing failure. Rotor bearing failure just simply means the rotor stops turning. Okay, it does not cause any type of metal deposit inside the X-ray tube. Let's see, the next one everybody got right. So X-ray production. So everybody got number 4 right. Okay, X-ray production increases when the mass increases. So everybody got that one. And then the next one, the power supply in the United States, this is just a fact-based question. It's 60 hertz. 60 hertz is the power supply in the US, 60 hertz AC. That is the frequency of our incoming power. Now, there's a difference in voltage, like household voltage can be 120 volts. Dryers will run off 220 volts. Our X-ray equipment, what's coming into the hospital, 240 volts, 440 volts. So there's difference in the voltage, but the frequency is the same. It's all 60 hertz, okay, 60 hertz AC. So that's what you should have had for power supply, 60 hertz. That's just a fact-based type of question. Let's see, the next one, X-ray production efficiency. What determines X-ray production efficiency? 3 things.
KVP, target Z, and the generator waveform.
Right. The generator ripple factor, the target material, the target Z, and the KVP. Okay. If you missed that one, the common answer for missing that one was ripple factor, target Z, KVP, and MA. Milliamperage doesn't have anything to do with the efficiency of X-ray production. Okay, MA has to do with the quantity, but not the efficiency of it. That would be the generator ripple, target Z, and the KVP. Okay. And then, let's see, the next one, everybody got the next one right. If you don't perform warm-up procedures, what could potentially happen? You can crack the anode, okay? And then the next one was a select 2, and it was talking about the line focus principle and what the benefits are. With the line focus principle, there is a larger actual focal spot, which corresponds to better heat dissipation. So larger heat dissipation, larger area for heat dissipation, and a smaller effective focal spot. So the line focus principle gives us a larger actual focal spot, which allows for better heat dissipation, and it gives us a smaller effective focal spot. It doesn't have anything to do with X-ray production efficiency. Okay, the fact that that anode's angle doesn't come into play with efficiency of X-ray production. Okay. The next one had to do with anode heel effect. What do you know about anode heel effect and the receptor size? Most pronounced with what receptor size?
Larger.
Larger. So the answer should be a 35 by 43 because that was the largest receptor size. That's when it's most noticeable, is with a larger receptor size. Okay. And let's see, number 10, the approximate average photon energy. If the KVP is set to 90 KVP, what is the approximate average energy? 90 KVP, most of the X-rays will have approximately how much energy?
1 to 90 keV.
That would be the energy range. This is for the average energy, because this asks what is the approximate average photon energy. Remember, the average photon energy is
30.
1/3 of the KVP. So a bulk of that corresponds to that Brem's peak. Most of the photons will have an energy that is 1/3 of the KVP. That's the average energy. So if you're at 90 KVP, the average energy will be around 30 keVs. So the answers I had for you were 32 keV, 57 keV, 69, or 90. So the average energy would be closest to 32 keV for these answers given.
I think the 32 threw me off a little bit on this.
What is the approximate average energy?
Okay, I think it just threw me off. I think I would have.
And the answers are far enough apart. Answer A was 32 keV. Answer B is 57 keV. So even if in your mind you're thinking 1/3 of 90 is 30, 30 is closer to 32 than it is 57.
Yeah, it just made me second guess myself, so that's why I didn't select that answer, but I should have.
Yeah, especially because approximate average, energy. So 32 is your best answer. Okay. 90 is not the correct answer because 90 would be the maximum energy, and this was asking for average energy, not maximum. Okay. So that makes a difference, average versus maximum. And then the next one, the highest energy photons in the primary beam, going to be equal to what? Highest energy photons going to be equal to the kinetic energy of the incident electrons. So for example, if you're at 80 keV, the electrons will have 80 keVs worth of energy. That means I will have photons that have 80 keVs worth of energy. So the highest energy photons in the beam are going to be equal to, the kVp that is set, which is what determines the kinetic energy of the electrons. Okay. The reason K-shell binding energy of the target material is not correct is because, remember, we always get Brem's X-rays. And their energy, Brem's X-rays, go from 1 keV up to whatever the kVp was that we set. So regardless of what kVp I'm at, I will always get Brem's, and the highest energy is always going to be equal to the kVp, which determines the kinetic energy of those electrons. Okay. The answer C, which was K-shell binding energy of the target material, that might have been a better, could have been a possible answer if this question was talking specifically about characteristic X-rays, but it was asking about the highest energy photon in the primary beam. So if I'm at 100 keVp, I do get characteristic, but I also get Brem's. And remember, the highest energy for characteristic is 69 keV. So if I'm at 100 keVp, the highest energy photon is 100 keV. Okay, not 69. So that's why that answer, K-shell binding energy, would not be correct. So you should have had kinetic energy of the incident electrons. And then the next one, decreasing the mass. If you decrease the mass, what will happen? Which of the following will happen? Well, if you decrease the mass, it has no impact on effective focal spot size. That was one answer choice. Mass does not decrease photon energy because mass has no impact on photon energy. So the only reasonable answer is you get a fewer number of X-rays. Okay. Individuals that missed that put D, and D was all of the above, which it can't be because the first two answer choices aren't correct. Mass only impacts the number of X-rays. And there was only one answer that talked about the number of X-rays. So fewer number of X-rays when you lower that mass. And then the next question, Brem's peak is equal to what percentage of the kVp? This is just a different way of asking the question that I asked about the approximate average photon energy.
Is it 30%?
It's 30%. Yeah, Brem's peak is equal to basically 30% of the kVp, thereabouts. Okay. And then the next one dealt with knowing the anode heel effect and how to place a patient. So X-ray intensity is going to be greatest towards the cathode side of the tube. So if you are imaging unequal thickness body parts, the thinner part would go towards the anode. So the thinner part under the anode, because the X-ray intensity is greatest under the cathode. So it was answer D. So X-ray intensity is greatest towards the cathode. You put the thinner part under the anode. Okay. So that was 14. And then the next one let's see, if an X-ray tube is set to 69 kVp, what percentage of the beam is characteristic? kVp is 69. Yeah, your choices were 0, 30, or 100%. So it's 0. If you're at 69 kVp, you do not have any characteristic interactions taking place. Everything is Brems. How come?
It has to be 70 or above.
You have to be set to 70 kVp or higher, right? Because the K-shell binding energy for tungsten is 69.5. So 69 kVp is not enough to break that binding energy. And then, let's see, next multiple choice question, the energy of characteristic photons. What determines the energy of characteristic photons? Is it electron breaking? Is it kVp? Is it binding energy or electric field interaction?
Binding energy?
It's the binding energy, the energy of characteristic photons. That's your key. The key word there is characteristic photons. If it would have said the energy of Brems, or just overall the energy, the overall energy of photons, then it would have been kVp. kVp determines the energy of Brems, because if I'm at 100 kVp, I've got Brems X-rays that are produced from 1 keV up to 100 keV. But this dealt with characteristic, and characteristic, it's dependent upon the binding energy, difference in binding energies. And then the last multiple choice question, you had to match the exposure factor to the emission spectrum change. If you change your mass from 8 mass to 16, so you've increased your mass, will the Brems amplitude decrease, will it increase, or have no impact? So your mass goes up, what happens to Brems peak or Brems amplitude? How does it shift?
Up.
Right, the amplitude shifts up. That corresponds to an increase in the quantity of photons. If the kVp is lowered from 85 to 65, what does Brems amplitude do? In other words, what happens to the quantity of photons? 85 to 65, right, Brems amplitude goes down. It decreases because kVp does impact the quantity. Okay. What about changing the SID from 72 to 40 inches? Does that have any impact on Brems amplitude? No, because remember, Brems amplitude, that correlates to the quantity of photons, and SID has no impact on the number of photons that get produced. Okay? SID does not impact photon production. It impacts receptor exposure, but it doesn't impact the number of photons that come out of the tube. Okay? So that one was no impact. How about changing the filament size from large to small? Does that impact Brems amplitude? Does that impact X-ray quantity? No impact. When we did that experiment in lab, you change the focal spot size, it's not statistically significant. Focal spot size or filament size only changes the actual focal spot size and the effective focal spot size, which is an image sharpness characteristic. It has nothing to do with the quantity of photons. Okay. So then we get into the short answer so that you know what I was expecting. For number one, if the kVp is increased by 15%, what do you do to your mass to maintain receptor exposure? You decrease it, right, by half. Okay, so I think y'all did pretty well on that. Increase kVp by 15%, decrease the mass by half. I think everybody was okay with that. The next one, what's the photon energy range for Brems? You had to include units of measurement. Whenever you're asked about photon energy for Brems, you need to make sure it is 1 keV up to whatever the KVP is. We do get photons produced with 1 keV up to the KVP that's used. If this wasn't asking about what comes out of the tube, because some of y'all put 10 keV up to, the KVP that was set. I was, I did give you credit for that, but it's not completely correct because we do have photons that have 1 keV worth of energy being produced at the anode. So this wasn't asking about what's the energy that comes out of the tube. It's just simply what is the photon energy range that's being produced. So I didn't count, I didn't count off for that. But you did definitely have to put that for the upper range, it's whatever the set KVP is. So if you're at 90 KVP, the range is 1 keV up to 90 keV. So I needed to know that you knew that upper range. Some of you put an actual stopping point and said the energy range is only 10 keV to 70 keV, which that's not true. Okay, unless you provided an example and said, for example, the KVP is set to 70, so the range would be 10 keV to 70 keV or 1 keV to 70 keV. So if you provided an example to back that up, that was fine. But if you just simply said, 1 keV to 70 keV or 10 keV to 70 keV, then that's not correct. Okay, you had to indicate that the KVP, what that was set to, is what does determine that ending point. Okay, because if I'm at 100 KVP, I have 100 keV photons. If I'm at 75 KVP, then I only have up to 75 KV for my mass energy.
What was the answer for this?
It's what's the photon range? It's 1 keV up to the set KVP.
So how many points was that question worth?
2 points.
Okay.
2 points. So like if you didn't put set KVP, then that would be a point off for not indicating that end range. I tried to give as much credit as I could and take off minimum points. Okay. So 1 keV up to the set KVP, meaning whatever KVP you set on the control panel, that will be the maximum energy for BREMS. And then the next one, I think you all did okay with this next one. Percentage of X-ray exposure that gives us X-ray photons, 1%, 99% heat. Okay, so 1% X-ray production. That was worth 1 point. And then the next one was a 2-point question. What factors should you consider altering to change radiation quantity? So it was 2 points. You got 1 point if you put mass, and then you got the other point if you said direct and linear, or if you explained, if you went into some explanation about that. Because some of you did explain how when you increase the mass, you increase the number of electrons that boil off that filament, that increases tube current. So you have more electrons that reach the anode to undergo X-ray production. So if you provided some type of explanation, that was fine too. But really, you could have just, you could have put direct and linear, and that would have been okay as well. So 1 point for mass, and then the other point for either putting direct and linear or providing an explanation of how that works when you do increase the mass. Does that make sense? Okay. And then the next one was 1 point, what interaction in matter does not ionize atoms? I think everybody got that right. That's coherent or classical. And then the next one was 2 points, what does the remnant beam consist of? So you had to put transmission or transmitted and scattered photons. So 1 point for transmitted, 1 point for scattered. That's what the remnant beam consists of. That's what exits the patient and makes it to the image receptor. So transmitted and scattered. Let's see. The next one was 2 points. It asked about backscatter radiation and how much energy. So you got a point for describing what backscatter means. So you needed to put something along the lines of backscatter means the X-rays go back the direction they came from. So if the X-rays enter the front of the patient, the X-rays will exit the front of the patient. Keep in mind, the X-rays don't go back up into the X-ray tube, though. Backscatter just means they go back out the front of the patient. And as far as the energy that they retain, backscatter retains, and this is just a fact, 2/3 of the original energy. That's how energetic X-rays are when they undergo Compton interaction. They just don't lose a lot of energy. Even if they backscatter, they still contain 2/3 of their original energy. So it was a point for backscatter and then a point for identifying 2/3. Okay.
So for this question, I put that the X-ray photons interact with the patient, but then they're directed back towards the X-ray tube. That's wrong?
Radiation that heads, what's meant by backscatter radiation? What did you say again?
I said X-ray photons that interact with the patient and then are directed back toward the X-ray tube. So that's wrong.
Did you put 2/3 for the?
Yeah, that I put.
If you put radiation that heads back in the original direction and 2/3, then that should be correct.
Okay, I'm just making sure based on what you said.
Yeah, that should be correct. No, that's fine. Maybe the reason you're asking, I did have one person in particular say that the X-rays go back into the X-ray tube. Is that why you were asking?
I just said back toward the X-ray tube, and I know you said it shouldn't be that.
No, that's fine. There's a difference between back towards the tube versus actually going back into the X-ray tube. So yes, okay, you're good.
What if we just said the angle of the scatter is 180 and travels backwards? I just remember that from the lecture when we discussed it in the lecture. I didn't say specifically to the X-ray tube.
No, that's fine. As long you didn't have to say back, because you said what again? It scatters.
Well, the scatter is 180 degrees and travels backwards when it scatters. I just remember that from the lecture.
Yeah. Yep. You were good. Yep, that was fine. That was fine. And then the next one was about explaining the photoelectric effect. It was 3 points. So for the first point, I was looking for something along the lines of you mentioning that K-shell's knocked out of orbit and that the photons absorbed. So something about K-shell being knocked out and the photon being totally absorbed. And for a second point, I was looking for you knowing that another electron from an outer shell will drop to fill the void, or that, a photon's released from that. So I was looking for something along those lines for those 2 points. And then 1 point for saying it's the white area. So that's kind of what I was looking for, just so that I knew you kind of had a basic understanding. So again, for the first point, I was looking for like K-shell being knocked out of orbit, or photon being absorbed. The second point, looking for you knowing that an electron drops from another shell, and that photons being released. So that's if as long as you were within those lines, then you got credit, for that. Okay, so I really wasn't that strict with that one. I just kind of wanted to know that you have a general idea of what's taking place here. Do you have any questions about that one with your wording?
Just if we said inner shell instead of K-shell, because
That's fine.
Okay.
Yep, that's fine.
On the one dropping down from another shell, but otherwise should be okay.
Yep. So anybody have any wording that they're not sure about?
I think for me, I didn't go into as much detail, but I think I knew what was happening.
Yeah, and if you know what's happening, then definitely put it down on paper, because it was asking to briefly explain it. So I needed to see certain pieces of information, and if I didn't see that, then I don't know that you know it if you don't have it written down. So I need to see that written out, so I would know that you have an idea as to what's going on. Okay. But I did, try to give as many, points with this type of, of stuff. It's not like anyone missed all 3 points off this. If anyone missed anything, it might have been like a half a point type of thing. Okay. And then the next one, I think everybody got this right. The biggest occupational threat to radiation exposure. What interaction is that?
Compton.
Yeah, Compton. And then I think the next one everybody got right. X-rays exhibit wave-like behavior when they undergo what interaction in matter? I think everybody got this. If anybody missed a line, then 1 or 2.
Classical?
That's the classical or coherent, exactly. That's when X-rays just kind of act like a wave. It just vibrates the atom. Okay? So that was 1 point. And then the next one had to do with calculating heat units. Calculating heat units. So this was 1 point. 4 exposures are made using 400 MA, 0.25 seconds, and 75 kVp. So when you multiply 400 times 0.25 seconds, that's 100 mass. So you say 100 mass times 75 kVp times 1.45, because that is the high frequency generator conversion factor. So 100 times 75 times 1.45 is 10,875 heat units. You had to take it a step further and multiply it by 4 because 4 exposures were being made. So the total is 43,500 heat units. If you stopped at just 10,875, I only took a half a point off, okay, because it was a 1 point question. So it was 43,500, okay, because it's 100 mass times 75 kVp times 1.45. Okay, so you okay with that one?
What'd you say the answer was again?
43,500, because it's 400 MA, 0.25 seconds, 75 kVp, and high frequency generator, which is 1.45 conversion factor. When you multiply MA in time, that gives you 100 mass. So it's 100 times 75 times 1.45. And that gives you 10,875. Then multiply that by 4, and that is 43,500. Okay. So you have to make sure you have your comma in the right spot too. That it's 43,500 and not like 435,000. You have to have that comma in the right spot too, or that would have counted off. Okay. And then the next one is 1 point. This was a mass distance formula. And you should have had around 9.4 mass, thereabouts. Okay. Sometimes depending upon how you round, if somebody put like 7.5 or 8 mass, there's no difference between 8 or 9 mass. But the way this formula should have been set up is you're using 6 mass at 48 inches. Now your SID changes to 60 inches. What mass do you use? So you should set it up as 6 over x equals 48 over 60 squared. and then work it out. So 6 over x equals 48 over 60 squared, and that should yield around 9 mass. Okay.
So I added, but you would round just because you can't enter 9.375 into the control panel. You didn't take off for that, did you?
No, no, would not take off for that. So if you were somewhere in the, neighborhood of 7.5, 8, 9 mass, you got it right. Okay. The number definitely had to be higher than 6 mass because you've increased your distance, so it takes more mass. Okay. Then for the next one, explain why photon quantity increases as the KVP increases. So it's asking why does photon quantity increase? What I was looking for is that when the KVP increases, the incident electrons have more energy, they have a higher kinetic energy, and if the electrons have higher kinetic energy, they can undergo more interactions. That's what I was looking for. That's why photon quantity increases. It's because the electrons have more energy. I did give a point, that was 2 points, but I did give a point credit if you said that the relationship is direct and exponential, but that's really not what the question was asking. I'm glad you did remember it was direct and exponential, so this time I let it go. But if you see something like that on the final exam, it's asking for explain why something happens. It's not asking for the relationship. So if you did put that, I did count, I gave you credit this time. If you put, there were some answers, somebody, I can't remember how many people, but had mentioned something about electrons coming out of the tube. Electrons don't come out of the tube. It's, X-ray photons that come out of the tube. So you have to make sure that, that your wording is correct. Because I usually, take a half a point off for something like that if the terminology is not right, because there is a big difference between electrons coming out of the tube and X-ray photons coming out of the tube. Okay, so you okay with that one? Does anybody have any questions about that, what I was looking for? Okay, let's see, the next one was 1 point, and I think I want to say just about everybody got this right, if not everyone. It's all focus radiation. All focus radiation is produced outside of the actual focal spot. The electrons are directed to the actual focal spot, but some of those electrons will hit elsewhere on the face of the anode, and it's called all focus radiation. So it comes down out of the tube, and it actually ends up imaging structures outside of the collimated field, and you had a picture of that in your PowerPoint. So that was all focus radiation. And then for number 32, it's a scenario, you're doing an elbow image and it requires 4 mass. So I'm telling you the mass that the elbow requires. You had to come up with 2 MA and time combinations to yield 4 mass. You had to keep in mind, okay, this is an elbow, so what would be appropriate MA stations? And remember, and we even did the worksheet, when you're around 200 MA, 200 MA can be used with a small filament and a large filament. Over that, like a 400 MA, that would require a large filament. And you have to remember, the key thing, this is an elbow. And we've said with extremities, you use that small filament. So you could have done 50 MA at 0.08, 100 MA at 0.04, 200 at 0.02, not 400. I did take off just a half a point, not a full point, because 400 MA means you are then having to use the large filament, and we are doing extremity work, and 400 MA is linked to the large filament. So this is based on that worksheet that, that we did. And then you had to defend your answer. And so you would want the highest MA in the shortest time. So if you wrote 200 at 0.02 seconds, that's what you would want to use because that's the highest MA shortest time. 100 MA at 0.04 would be, yes, it gives you 4 mass, but that is it's a longer time. So wanted to see if you remembered about using the highest MA shortest time because of motion. For the most part, you all did okay, with that.
So how many points total would you take off then? Because I did do 400 MA, and I said I would use that one because it was the shortest time.
Just 0.5. It was 2-point question, so it was just 0.5.
Okay.
So a quarter of a point. Because I'm glad at least you came up with with a combination. But just want you to remember those higher MAs are linked to larger filaments. And I know in reality, most of our equipment, you are not independently setting that, but it is something that you do need to know and be aware of because you may end up using some of that equipment somewhere. And then the last 3 were images. If you need to see the image, I can do a screen share. But you had actually, let me just go ahead and show you. You had the emission spectrum, and it was asking what factor changed to cause this. And the giveaway, the easiest giveaway is the termination point. So it's KVP. These were done with 2 different KVPs. There's a change in the amplitude shifting left and right too. See how this one, the peak is further to the right, and here the peak is to the left. So that also corresponds with a change in KVP because my average energy is lower with a lower KVP. My average energy is higher or more to the right with a higher KVP. The up and down amplitude shift, corresponds to a quantity difference. And when you lower your KVP, you do lower the amplitude, you do lower the quantity. So the peak not only shifts down, but the peak shifted to the left, indicating that was a KVP change. So you okay with that one? So that was a point. And then your next image that you had to look at, you had to figure out what chart to use. This exposure is safe, and this is the chart that you should have used. It was 300 MA at 0.1 second and 90 KVP. It was 10,000 RPMs and a 0.6 focal spot. So if you're at 90 KVP, you're somewhere in this neighborhood. And if you're at 0.1 second, so 90 KVP, 0.1 second, so my intersection point is going to be somewhere around here. But it was at 300 MA. I am below the 300 MA curve, so that is a safe exposure. So that was one point. And then the last one was the anode cooling chart. And about how long, if you have 150,000 heat units applied to it, how long will it take to cool? So the difference between here and here was around 12 minutes, 12 and a half minutes. So if you were somewhere in that neighborhood, then you were fine. I think everybody got that. So that was one point. And then for your bonus, another name for coherent interaction, classical. If you put Rayleigh or Thompson, then that was fine. You got a point for that. And I think everybody got that one. And then the last bonus question, you had to be careful as far as the way it was worded. And it was decreasing the KVP by 15% has the same impact on receptor exposure as doing what to the mass. So this is not asking you what do you do if you decrease the KVP by 15%. It's asking you what type of impact does it have on receptor exposure? So if you decrease the KVP by 15%, that has the same impact on receptor exposure as reducing the mass by half. Okay? That's why if you do reduce the KVP by 15%, you have to double the mass in order to maintain receptor exposure. This question wasn't asking about maintaining receptor exposure. So this question wanted to see if you were understanding the impact between KVP